Good morning, everyone. So we'll continue the discussion that we started at the end of our lecture yesterday, the last one, about supersymmetry. So now, since, of course, 5 lectures for beyond the standard model of physics is a very short time. So what I will do, because this is essentially a last lecture, so instead of reviewing a bunch of things superficially, I'll try to sort of go deeper into some of the concepts which are very important. But as I said, I mean, you can ask me any question, you can stop me anytime, whatever. Or so we said that when we have the supersymmetry, the immediate prediction from supersymmetry is that every particle, known or unknown, doesn't matter, must have a partner under this supersymmetry transformation. And as we said, the unusual thing about supersymmetry is that these partners, they have different spin. Okay? And this is very different from any other internal symmetry that we are used to. Now, this is not surprising because supersymmetry, as we said, is not an internal symmetry. It's a space-time symmetry. It's an extension of the space-time symmetry, sort of along the same lines as idea about having extra dimensions, except, as we said, this dimension is now fermionic. Okay? So now let me try to reiterate what it means again on this, and what it means to break supersymmetry and why this mass splitting among the particles should happen when we break supersymmetry. So now, as we said, so we have, let's say we have an electron, let's call it psi, okay? And then we said this electron should have a partner which has which has a spin 0. At least this has to be a boson. As a matter of fact, it turns out to have spin 0. In supersymmetric limit, they should have the same mass. Okay? Now, let's try to understand on some simple qualitative examples. Let's try to develop some intuition. What are we talking about when we're talking about this extra fermionic dimension, shift in this dimension, etc. Okay? And for this, let's make an analogy with a problem with all of you are very familiar. Okay? So again, let's introduce this story with Alice and Bob, okay? And then let's consider the following setup. So let's consider a 3-dimensional space, okay? Nice, familiar 3-dimensional space. And so we split this, so we introduce a coordinate system in this dimension, okay? So we have z, and then we have x and y coordinates, okay? Now let's consider 2 observers. So let me single out xy plane, okay, as a physical space in which Alice lives, okay? So Alice is an observer in this 2-dimensional space, okay? So she lives on this xy plane, and she can do. Otherwise, she is not restricted. She can do any measurements she wants on this xy plane. Okay? And then there is a Bob, and he is a 3-dimensional observer. Okay? So Bob can perform 3-dimensional measurements. So now, Alice, she knows that there are 2 dimensions that she can measure. She has a ruler. She can measure 2 dimensions. Okay? And let's say the only difference between them is that Alice cannot measure directly the extra coordinate, z, okay? Otherwise, she is fine. Okay, so now, imagine that in this 3-dimensional space, we have a vector, okay? There is a vector that lives in this 3-dimensional space, okay? Some vector, whatever. Let's call it A, okay? So this is a 3-dimensional vector. So let me denote this 3-dimensional vector by this symbol, like tilde with arrow, okay? Now, so Alice can measure, because she's a 2 plus 1 dimensional, two-dimensional observer, okay? Of course, time is common. She can only measure projections of this field, of this vector, on this two-dimensional space, okay? Now, so this vector, of course, it has 3 components, right? It has z, x, and y, okay? Now, the group of symmetries for Alice are two-dimensional rotations, okay? So she can do rotations in her plane. This is analog of her Poincare group, okay? So Alice has rotations in two-dimensional plane, so she can rotate this plane. And she can classify all the objects under their properties under this rotation, okay? So for her, there is this rotation group. This is her Poincare group, analog of Poincare group. And she can classify everything in terms how these objects transform under this rotation, okay? Under this group, this symmetry. Now, what will she discover? Because she can only measure projections on two-dimensional surface of this vector, she will, by measuring exactly the same thing, the same three-dimensional vector, she would tell you that yes, there is this field or a particle or whatever you want to call it, okay? But actually, these are two different stories, two different fields. Why? Because a z component for her is a scalar. Obviously, the z projection of this vector, okay, a of z, is not transforming when she rotates her two-dimensional space, right? Is invariant. So for her, it's a scalar. So she can call it phi. Okay. And the other two guys, of course, they form a vector, and she can call it v. Okay. All right. So in other words, a high-dimensional vector, which I called tilde whatever, okay, splits. From her point of view, splits in a scalar, with, so let's take so in this coordinate system, let's introduce unit vectors, which are vectors in z direction, x direction, and y direction, right? So this is a vector in z direction, okay? In fact, like this. And then there is simply a vector v, okay, for her. All right, so now, then she can do different measurements. For instance, she can measure the spin of these particles, she can measure the mass of these particles, spin we already measured, mass of these particles, and she will discover that they have the equal mass, okay? So obviously, she will completely reconstruct a new symmetry under which a scalar and the vector go into each other. Now, she has no idea that she lives in three-dimensional space. So for her, this symmetry would be some mysterious symmetry, which is a symmetry between a vector and a scalar. But that doesn't matter, because she would reconstruct exactly the same symmetry that Bob sees from the point of view of three-dimensional observer. For Bob's point of view, this is just a vector, three-dimensional vector, and that's it. So the different components, they go to each other. Three-dimensional space is rotationally invariant, okay? So therefore, all these particles will have the same mass, right? Now, let's make the analog with, so now suppose, so in other words, now suppose Alice wants to, so now suppose we are in this situation, okay? So now we are now that we are trying to reconstruct supersymmetry at LHC to measure, we are in the role of Alice. Because we measure different fragments of the superfield which lives in the super dimension, okay, in the super space. And then we see that actually we have only, so far we have discovered only some fragments and the others are missing, okay? So for instance, imagine that in this situation, Alice only sees a scalar and the vector is missing, okay? This would mean that this symmetry is broken, okay? Now, what it means for a vector to be missing? In particle physics, when something is missing, so when we say something is missing, we always refer to some energies. In other words, we are saying that a given state is inaccessible at given energies. So this means that the vector is heavy enough so that she cannot excite it in her experiment. So now, how can we achieve this situation? How can we achieve mass splitting between the symmetry partners? Well, here, this would happen automatically if the rotation invariance in 3 dimensions is broken. So for instance, there could be a magnetic field. Okay? So imagine that there is a magnetic field. Let me draw it in a different color, right? Imagine that there is a magnetic field in z direction. Okay? Let's call it B. Now, of course, if there is a magnetic field in z direction, and this field, this vector field, has some interaction with the magnetic field, okay, let's say it has a magnetic moment. Obviously, there will be a level splitting. The different orientations with respect to this magnetic field will not have the same energy. So from Alice's point of view, this would mean that this particle phi and particle v, they will have a mass splitting. Now, for instance, right, if so of course, how precisely the masses will split depends how this field interacts with the magnetic field. So for instance, if the interaction is something like this, so let's say interaction energy functional, will depend in general on some scalar product between the magnetic field and the vector A. So for instance, you will have a scalar product between B and A, okay? And it can have plus or minus sign. Let's take square here, just for definiteness. It can have any form. Now, so if the sign is plus, this means that the state, if the sign is plus, then this term, to minimize this term, the scalar product has to be 0, okay? The lowest possible energy is when it's 0, because the sign is plus. In other words, this means that A vector wants to be perpendicular to the magnetic field, okay? If A vector wants to be perpendicular to the magnetic field, this means that the scalar has higher mass than the vector from the point of view of Alice, right? Because if you put if I have a magnetic field vertically and I put vector like this is my scalar, because this is when Alice sees a scalar. But the scalar is unstable because it wants to decay into a vector, okay? So vector is lighter because it wants to be perpendicular, okay? So if sign is plus, this is what is happening. If sign is minus, the story will be the other way around. If sign is minus, the vector A would like to be aligned with the magnetic field to make it more negative, the whole story, right? So in that case, scalar will have a lower mass. So as you see, depending how you break the symmetry, there will be an effective mass splitting as seen by any observer. For Bob, this is a perfectly three-dimensional story. He just will tell you that, okay, yeah, there is a vector and there is a magnetic field, and obviously there is a degeneracy is broken. So orientation, some orientations have lower energy. From the point of view of Alice, she may be completely mystified because she sees that there is a symmetry, but the partners, they have different masses because symmetry is broken because of this background magnetic field. So in other words, your vacuum, in this case, our vacuum has a magnetic field in it. Break symmetry is not invariant on the symmetry transformation. In this case, you have a mass splitting, okay? Now, let's generalize this to supersymmetry. Now, we literally we'll take this picture and literally generalize it to supersymmetry, okay? That is with one-to-one analogy, okay? Now, in supersymmetry, we had psi and phi. Now, they will play the role of phi and v, okay? Since phi is a scalar, let's identify phi with phi anyway. And we can identify psi with v as an analogy. Of course, the spins are different, okay? And how does this happen? Again, the same story, okay? Again, let's consider a situation with Bob and Alice, except that now we have this dimension. Instead of z-axis, we have a theta coordinate. That's the only difference, okay? And instead of xy space, we have full three-dimensional space, okay, x, y, z. So this is normal four-dimensional, this is normal three-dimensional space that we live in, x, y, z, okay, everywhere. So Alice is again here, okay. Now we are Alice, okay, and Bob is maybe somewhere there, we don't know, okay. Now, again, it's the same story. Now we have a field that lives in this high-dimensional superspace, okay? Now it's a superfield, S. Okay, it doesn't have to be a vector. We can take it to be a scalar. And there is a superfield, which, of course, it depends on the usual coordinates, x mu. X mu's are here. This is the x mu space, right? And it depends on theta. What Alice measures are x mu projections, the components of this field. Now, the analog of the rotation in the previous example is now a full Poincare group, okay? So now we live on a subspace. This subspace has a symmetry under full Poincare group, Lorentz boosts and rotations and shifts. But in reality, we live in the superspace. So when we measure, when we do our measurements, we see different components of the superfield. In other words, this analog of this expansion in the previous example, okay, now will be that we have a superfield, theta and x mu, and we measure different projections of this superfield on our space. So there will be one, and then there will be another one with theta. This will be a fermion, psi of x, and so on. There could be other components, okay? So you see, it's exactly the same story. The way the vector was decomposed into scalar and the vector, okay, from the point of 2 plus 1 dimensions. The superfield is decomposed into a scalar, a fermion, and God knows what. Depends on your representation, okay? And what Alice measures, she measures this. We measure this, okay, psi and phi. And for us, these are different particles. Just exactly in the same way as in the previous example, the scalar and the vector, from her point of view, were different particles, different fields. Okay? Now, so far the analogy is like 1-to-1. There is absolutely no conceptual difference. Well, there is one difference, of course, which is crucial, which makes all the difference, is that theta is a fermionic coordinate. Okay? So, because theta is a fermionic coordinate, as we said in the previous lecture, it anti-commutes with itself. It's a fermion, so it anti-commutes with itself. It's so-called Grassmannian variable, okay? It's not an ordinary number. And because of this, you know that if you have a theta which is a simple fermion, let's say Majorana fermion, if you introduce it as a Majorana fermion, then this expansion has to truncate. In other words, number of independent components of the superfield is finite. Okay? It has to truncate maximum at 4 if I have one Majorana spinor. This is so-called n equals 1 supersymmetry. But then it turns out that you can further improve this story by splitting the superspace into two different spaces, so which have different chiralities. Why? Because since theta is a fermion, it allows for you to define chirality. Actually, you can define left-handed theta's coordinates and the right-handed ones. And correspondingly, you can split the superspace into two subspaces. And it turns out that individually, each subspace is on its own a representation of the supergroup. This is a technicality. Unfortunately, I don't have time to go deep into it. But it's just the concept. This does not affect this conceptual discussion. Okay. So in that particular case, when we talk about so-called chiral superfields and chiral spaces, this expansion actually truncates at 2. Because you split 4-dimensional space into 2-dimensional spaces individually. So in each 2-dimensional spaces, you truncate your expansion at 2. So there must be another term here in this expansion, which is theta theta, so-called f. But it turns out that this field is non-dynamical. It does not propagate. Okay? It's an auxiliary field. You can, in other words, this field on its own, you can fully express it in terms of the other fields. Okay? It doesn't carry any information. Okay? So therefore, we can forget about it. And we can think in terms of expansion in being truncated effectively at 1 theta. Okay? Now, so far this is great. So this picture will tell you that if this were the story, then, as we said, if I identify psi with an electron, immediately I'm led to a conclusion that there must be a scalar partner of the electron, so-called selectron, scalar electron. And of course, the scalar partner should have the same mass, by the obvious reason, just exactly in the same way how the different components of the vector had the same mass, because rotation invariance in full three-dimensional space was unbroken. In this example, rotation invariance in the full superspace is unbroken. Now, because we don't see this electron, and as we discussed, this existence of this scalar electron, etc., scalar partners, would be crucial for canceling quadratic divergences into the scalar masses. Okay? Now, since we don't see the superpartner, what is the conclusion? The conclusion is that the story is with the magnetic, the analogy is with the magnetic field. Okay? In the other words, there is some analog of the generalized magnetic field in the superspace, which makes sure that different projections of the superfield are not energetically equivalent. So as a result, it's more costly to have a scalar electron around, okay, than the electron around. So in the other words, the scalar electron must be heavier. But the story is exactly the same. In the other words, there is a field in the superspace, like magnetic field, which has an expectation value and which interacts with other superfields. And because this superfield has an expectation value, exactly in the same way as the magnetic field was splitting different projections, okay, different components, different projections on a given direction, this splits different projections on a given super direction, okay? Now, it turns out that, I mean, who is this so the whole question about supersymmetry breaking, and there is this whole industry, and it's a very deep question. It's a, I don't know, there is a, it's a whole story. Essentially boils down to who is this field, this mysterious field that precisely breaks this rotation in this superspace, and how does it couple to the ordinary, how does it couple to other superfields, to ordinary superfields. Okay? In other words, the mystery is about to find the analog of this interaction in the supersymmetric case. Okay? What is the magnetic field that splits the states? That's the whole point. And depending precisely on that nature of whoever breaks supersymmetry, the field that breaks supersymmetry, this precisely will define what is the spectrum of superpartners that we should see at LHC, if we will. Okay? So, in other words, it's obvious, right, that in this example, in case of magnetic field, it was very simple. You put a magnetic field, you know that even if you start with a vector projection, which is perpendicular, if sign is plus, for instance, right, if sign is minus, having a vector perpendicular to the magnetic field is energetically not favorable. It will decay into scalar, because it will want to be aligned with the magnetic field, okay? So in other words, the heavier particle, superpartner, will be unstable and decay into the lightest one, okay? Unless you do some special tricks, for instance, you can manage to have interaction which is more complicated so that there will be a lightest partner to which everybody will decay, okay? And that guy will be stable because of some symmetry. We can arrange this also in the magnetic field, okay? So depending whom you identify with a superpartner. So, in other words, this is the whole point. And now, it turns out, so in other words, let me write it here. So let's call this mysterious superfield X, okay? The analog of magnetic field, X. So it turns out that by consistency of the theory, and by consistency and by the fact that you want to break supersymmetry without breaking Poincare invariance. Of course, we could have, you see, it's the same thing like here. So Bob, in this example, could have broken rotation invariance in 3 dimensions in different ways. he could have broken rotational invariance in such a way that also two-dimensional rotational invariance is broken. So for instance, if you have two magnetic fields which are at some angle with each other, then there is no rotational invariance whatsoever left, okay? So in principle, you can break symmetry completely. So that in this case, there would not be a scalar and a vector, but there will be complete non-degeneracy in each component, okay? Now, he chose the magnetic field to be in the z direction because he cared about Alice to have unbroken two-dimensional rotational invariance, okay? Now, we do have unbroken Poincare invariance. Again, it's the same story. So we want to break supersymmetry without breaking Poincare invariance. So that's why whatever this analog of magnetic field is there, it has to develop an expectation value such that this expectation value from our point of view is a scalar, okay? It's a scalar, but scalar which breaks supersymmetry, which is not invariant under supersymmetry. Okay, so anyway, so the story then would be that you have this analog of the magnetic field X superfield, and this superfield couples to ordinary superfields, which contain quarks and leptons, okay? So there is some interaction between S and X. So quarks, leptons, they live here, okay? And this is a mysterious guy. Now, it turns out that if you want to do this, for the reasons that I don't have time to explain, this superfield X has to have an expectation value on the last component of its own. So in other words, if I take superfield X, which is function of theta and x mu, right, and I expand it in components, eventually I end up with the highest term. In the case of a chiral superfield, this will be theta squared, theta f. In case of so-called real superfields, okay, this will be theta square, okay? And so this has a name, just a historic name. This is called an F term, and this is called a D term. So one of those terms is the only one which is permitted. In other words, one of those terms is the analog of the magnetic field looking in the z direction in the case of Bob, okay? If you give expectation value to somebody else, you will also destroy Poincare invariance, okay? Either you, yes? No, theta, as I said, right? So depending on, theta has a chirality which you can define, okay? Theta is let's introduce it as a Majorana spinor, okay? So 4 components, 4 real components, okay? So then you can, if this has 4 real components, I can define chirality, okay, by forming out, let's call it theta plus minus, 1 plus minus I gamma 5 over 2 theta, okay? So in other words, out of Majorana spinor with 4 components, I can form 2 Weil spinors with different chiralities, okay? And as I said, they are, when we talk about irreducible representations of the supergroup, okay? So there is a possibility to go to the chiral superfields. In other words, to define chirality, this splits your superspace in left chiral, right chiral, or simply real, okay, which have equal contributions from both chiralities. Now, the superfields operating in each of these subspaces are irreducible, okay? So, in other words, this is what I said. If you are choosing to have a chiral superfield, then the expansion has to truncate at 2 thetas, okay? Why? Because chiral superfield is always function of plus or minus. And so, of course, theta plus is the last thing you cannot write 3 times theta pluses. That's impossible. By the same reason, because they are anti-commute, okay? But if the superfield is real, then you can write 4, okay? So in other words, depending whether you have chiral superfield, the 4 is the absolute maximum for n equals 1 supersymmetry, because if you have 1 Majorana spinor, it has 4 real components, and that's it. Theta into the 5th power will be 0 by anti-commutation properties. For chiral, it already stops at 2, and so on. Okay, now unfortunately, these are technicalities which I would love to explain, but the time is really running fast. I don't know what's wrong with this clock, but anyway. Okay. So basically, this is the story. The story is, who is this guy who breaks supersymmetry? Actually, It turns out that it's not really easy to break supersymmetry. By some reason, it's much harder to put this analog of the magnetic field in the superspace than this ordinary magnetic field in case of this example, this simple example with Alice. But it's just harder to make it compatible with phenomenology. But you can. I mean, there are great ideas around, and there are great models around which actually break supersymmetry, and they predict things. Because they specify certain fields, then the whole game about this supersymmetry breaking is to make some predictions what kind of splitting among the superpartners we should see at the colliders, okay, at LHC. And there is this whole industry, which obviously I cannot cover. If you have any questions, however specific, please feel free to ask. So in other words, there are two types of breaking. This is F-type or D-type of breaking. It turns out that even if you use D-type of breaking, you still need an F breaking, because otherwise the gauge partners of the ordinary fermions, ordinary vector fields for W and Z bosons, for instance, or gluons, they will not get a mass, okay, if you only have D breaking. And so you need F breaking also somewhere. So there must be a superfield, and this is good news because this makes it more predictive. So we know that there must be an F term which is non-zero somewhere around. Now, the thing is, however, is that the field that is responsible for supersymmetry breaking may be extremely, itself, this field, may be extremely weakly coupled to us. In fact, the preferred models are precisely where this field itself is extremely weakly coupled. In other words, to think in terms of magnetic field, imagine that you have a very strong magnetic field, but the particles that correspond to the excitations of this magnetic field, right, these electromagnetic waves, they are extremely weakly coupled to us, okay? So in other words, most likely LHC will have no way to probe directly this sector which creates this breaking of supersymmetry. But LHC will have, if supersymmetry has to do with solving the hierarchy problem, LHC will have possibility to probe the spectrum of superpartners, which would be a fantastic thing anyway. So I promise if we see superpartners, in the first approximation, nobody will care about not seeing X, okay? It will be such a big deal. Anyway, so this is as far as supersymmetry breaking is concerned. Now, then supersymmetry brings a certain number of things with it, okay? Now, for instance, one of the things I would mention, actually there was a question yesterday, is that, you see, in the standard model is a very interesting structure from the following point of view. Of course, it's very interesting because it's real, but that's another story. But it's very interesting from the following point of view, that it automatically has a built-in symmetry in form of baryon and lepton number conservation. So in other words, the point is that the moment you write down a most general gauge invariant Lagrangian for the standard model, okay, renormalizable Lagrangian for the standard model, it's automatically baryon number preserving and lepton number preserving, okay? This is a pretty big deal because in a sense, of course, it's a post-diction, but baryon and lepton numbers so far are conserved as far as we can see. So standard model automatically tells you that baryons and lepton numbers are conserved. There are some non-perturbative effects in the standard model which extremely weakly violate certain combination of baryon and lepton number, B plus L. But they don't lead to proton decay. And so in other words, within the standard model, proton is safe automatically. With supersymmetry, okay, this is no longer the case. The moment you write down supersymmetric MSSM, minimal supersymmetric extension of the, and if you just require gauge symmetry, absolutely there is no reason to conserve baryon or lepton number. In fact, there are huge there is big number of interactions explicitly, renormalizable interactions within MSSM, which immediately violate baryon and lepton number, and they would destroy proton immediately. Okay. Now, so the question, so now this fact is there. So the question is, what do we make out of it? Okay. Now, on one hand, it's great when theory brings some new effect. obviously, right? If theory tells you that proton is no longer stable, that's a prediction in some sense. So that's great. We have to go out and look for the proton decay. The problematic part, well, not the problematic, but the mysterious part is that this breaking is, unless you do something else, this would be order 1, and of course it's ruled out, okay? Actually, already from our existence, proton is very long-lived. Because if proton had a lifetime, I don't remember what is the precise number, I think 10 to the 20 years, or 10 to the 19. If the lifetime was shorter than that, I mean, we would be, evolutionary, we would be sort of okay, except that the radiation would be so high, even from the proton decays from our bones, that so we would not exist. So already say proton is pretty stable. This is what I want to say. Okay, anyway, but so the question is, and this is a mystery in the standard model. Why this proton, why this baryon and lepton number violation is suppressed? So of course we can do it technically, as you know, that we can impose a symmetry, so-called R parity or so-called matter parity, and this symmetry takes care of it. But you see, you can look in two different ways at it, because symmetry is fine, but why would nature need this symmetry? Why would nature have to care about proton being so stable? It's a big question. Now, again, I don't have, of course, time to talk about grand unification, but actually it's interesting that in some versions of grand unified theories, like SO10, for instance, matter parity is automatically a part of the gauge symmetry. So, for instance, in SO10, at least certain versions of SO10, the low energy minimal supersymmetric standard model would automatically be endowed with this matter parity symmetry just from the gauge invariance, okay? So, you see, these kind of things may be different. So, these kind of things are very important because they can serve as a guideline, indirect guideline, for finding unified theories and for additional motivations for selecting among different unified theories, okay? Now, again, as I said, I have to sort of converge on discussing supersymmetry here because we have like extra 5 minutes left. And, but again, I'll be happy to answer your questions. Now, finally, in these 5 minutes, I want to just end up with some kind of give you some examples of open questions about the BSM, and just to illustrate, you know, how I mean, there may be, just to illustrate that there could be surprises there, okay? And it's really important to think about different possibilities, okay? So for instance, I don't know, let me pick up this, there were questions here, and then some of you asked me then after about this possibility of stable black hole production and things like this, okay? Or possibility of producing black holes which are pretty much classical, okay? And so, as we explained, in the minimal scenarios in which you assume for instance, you assume you have an extra dimension and there is no breaking of translation invariance in this extra dimension. In the other words, Alice and Bob, we had this example, right? Remember, we had again this example with Alice and Bob. Bob was 5-dimensional or whatever dimensional. In the example in which there is no breaking of translation invariance in the extra space, then Alice and Bob, they measure exactly the same 4-dimensional gravity, okay? And so in those cases, as I try to emphasize, at best we have a chance to see bottom of this black hole tower, okay? We have a chance to see something which we will see as a strongly coupled, strongly gravitating resonances, but these objects will not be reliably classical. There will be some pretty much quantum objects which would decay very fast, and you cannot really distinguish their decay from, you cannot really call it an evaporation. It will be literally like a decay. Of course, it would be a great thing if we probe them, okay? But you can ask the question, I mean, can I deform my theory, go beyond the minimal things, so that in principle I could produce something which is a different possibility, which would be something like more classical, okay, and more stable. And the answer is, well, yes. Well, the question is open, but in principle you can think about possibilities in which the translation invariance in extra dimension is broken. In the other words, in this situation, Alice, remember the force, right? Remember the force law was that a force that Alice would measure would be number of available messengers, okay, times the Newton's force. Now, if translation invariance is unbroken in the extra space, then this is exactly the same story for Bob, because number of messengers that couple to Alice is exactly the same as number of messengers coupled to Bob. But if translation invariance is broken in the extra space, and usually it is in this kind of models, because we have localization of brains, remember it's even already there, and stuff like this, then force that is measured by Bob may be different. Why? Because the number of messengers by Bob could be much larger than number of messengers to which Alice couples. Now, if this is the case, then some really exotic possibilities open up, because then you can produce a state which, if it drifts into the extra dimensions, from Alice's point of view will be a weakly gravitating object, but for Bob's point of view, it will collapse into something which is a pretty quasi-classical black hole, okay? And then, of course, there are all these very interesting questions. What happens in this case, okay? Whether you can have a sensible quantum gravity theory, which gives you this kind of possibility. I mean, effective field theory, for sure you can have. We can write it down in no time. There's no problem. But the question is about fundamental consistency. If yes, then in principle this possibility is open, that you could produce something which, because the strength of gravity for different observers is different, because the local strength of gravity changes, you can create objects which, from the point of view of Bob, a bulk observer, would be pretty quasi-classical black holes, and therefore pretty long-lived. Whereas from the point of view of four-dimensional observers, they will not look like black holes because they don't touch the horizon of that object. They will look like as massive particles, okay, which are very long-lived. And then are, of course, all these exotic questions, whether this guy can grow, and usual stories that you were asking, etc. Anyway, so let me converge. What time is it? I don't see the clock. Is 12. Okay, so I should finish, yes. All right, so let me finish with this BSM discussion. I mean, unfortunately, we had no time to go to Technicolor. But anyway, if you have questions, I'll try to address them, okay? Thanks. So there is a discussion session now, right? Oh, okay. Immediately, right?
Yeah. People get up.
Yeah.
Hello. We have a short announcement here about a book presentation from the library. If you just give him a few minutes of attention.
Yeah, there will be a discussion session now.
Thank you very much. So I invite all of you to come this afternoon to this very room at 3:30. Lynn Evans, leader of the LHC project, is going to present the book he edited. He's just out now. EPFL Press, The Large Hadron Collider, A Marvel of Technology. In this room, 3:30 today. Books will be available for sale, for signature, and the presentation promises to be very interesting. Thank you very much for your attention. Thank you.
Okay, if you have a question, please raise your hand high and I'll run with the mic.
Hi, I have a question about the beyond standard model part. In your first diagram of hyperspace with Alice and Bob, on that piece of overhead, you wrote down the minimization of energy equals plus or minus BA and stuff. How would you fit that with the four-factor notation that we know now, x naught as the time and x123 as the space?
How would I fit that
Fit the four-factor notation that we're using now, x naught as for the time coordinate and then x123 for the space coordinate into that idea?
Oh, sure. I mean, there's no problem. It's, you are asking how would I generalize this to the four vector notations? There is no problem. You tell me what you want to use to break rotation invariance, and you can, for instance, like I don't know, if you want to break rotation invariance by magnetic fields, okay? So you can always, so all you have to do is to truncate this with some vector indices, okay? So for instance, now, of course, if you have only one real vector, this particular thing will be 0 for one real vector. But of course, if you have two, this is immediately non-zero. Here's an example when you break rotation invariance, but it's a full for index formalism, okay? But in my case, I was, I mean, this was just an illustrative example, absolutely non-relativistic, to illustrate the concept of symmetry breaking by a background, certain background field, okay? Now, you can use other means to break rotation invariance, not just magnetic field. You can have anything could break rotation invariance. But yes, I mean, there's no problem. You can write very simple, nice models which, yeah, if you couple to magnetic field, they break rotation invariance. So for instance, I don't know, when you couple to spins, right, if you have an electron, this is precisely how the magnetic field gives you usually the splitting of projections. And in case of, this is the magnetic moment coupling, right? So this is precisely would be what I wrote, B, with a magnetic moment, with A, but A would be a magnetic moment of whatever field you want to introduce, for instance. Okay, I mean, there are plenty of possibilities.
Okay, all the way over there, all right. Microphone's better.
So, well, basically, I asked you the same question earlier, but how would you have a superfield with, say, like a gauge boson or graviton?
Oh, very good. Yes. So the question is that he's asking is that where are the gauge bosons coming from, right? The chalk is. We are chalkless, but anyway. So, so it turns out that to accommodate gauge field, vector field, okay. The good thing. So as I mentioned, the superfield, superspace, because it involves the fermionic coordinate, you can split it into different subspaces, okay. So you can. So there are three important ones: the subspace of chirality left, chirality right, and vector-like. Vector-like, I mean that it has no chirality. It just depends on real theta, for instance, okay? So let's take such a superfield which lives in a real superspace, in other words, non-chiral, okay? So then this guy will be function of x mu, and theta, where theta, you can think of theta as real Majorana fermion, and this guy, of course, is also real, okay? So then it turns out that the vector is living in as one of the something that is seen as vector by Alice, by us, is one of the components of this superfield, which is otherwise would be a scalar from the point of view of Lorentz transformations. Now, why? Because if I expand these terms, right, I will have a scalar, et cetera, et cetera. There is in the expansion, there is a term which has gamma mu in it, okay? Gamma mu, actually gamma mu, gamma 5, or something like that. And of course, this term, because it has an index, the corresponding coefficient is a vector, okay? So that's how the vectors appear, okay? So typically the vectors appear in this way. So in other words, all the known particles, in order to describe all the known particles, fortunately, you don't have to go to superfields which have Lorentz indices. The scalar superfields are completely enough. So the superfield of plus minus chirality, which depend on actually the complex coordinate and theta plus minus, and the real one are completely enough. And the vector is living in the real one, okay?
Wouldn't you have way too many particles? Like you have
in the vector,
a
right?
spin 2 and then...
No, spin 2 doesn't enter in the vector one. You can check it. Spin 2 doesn't enter.
Okay.
The maximal spin, if I expand V, the maximal spin will be 1, okay? So you could, for instance, this is another point. In principle, yes, you could go to higher supersymmetries, okay? And for those, eventually you would start ending up with higher spins. That's, in fact, is used as one of the arguments against very high supersymmetries, okay? The number of supersymmetries that you can incorporate, therefore, has limits. It's n equal 8. Higher ones would introduce higher spins, and actually we have very good arguments to think that the higher elementary spins in field theory do not make sense. Okay. Then you have to go to string theory, because then you need an infinite tower. But in any case, in your question, to ask your question, no, there is no higher spin than 1 in these superfields.
But there will be like pseudo-scalar and...
Yeah, there will be plenty of things.
Okay.
Yes, of course, as I said, unfortunately. So what vector will be plenty of things. Then you can fix, some of those are unphysical in the sense that you can remove them by gauge symmetry, okay? And the remaining ones, some of those are again unpropagating. You can express them with respect to the fields. And actually the physical ones, the bottom line is this, okay? In the vector field, the physical ones that survive at the end of the day, V, gives you the physical fields, which are gauge bosons that we see around us, and their fermionic partners. These are the only two propagating degrees of freedom, okay? So in other words, vector superfield houses what do we call gauginos, the gauge partners of W bosons and gluons and photons, and the vector fields themselves, okay? Right.
Okay, next question, please.
So if we break supersymmetry, we get different masses for the particles and their superpartners. How do we guarantee that the hierarchy problem is still solved? So how does this soft symmetry breaking work?
Very good, yes, excellent. So the question is, actually it's a very good question. The question is, we, as I argued, we introduced supersymmetry to solve the hierarchy problem. Remember? Because what I said is that if I have a scalar diagram, so there was a scalar running in the loop, there was a scalar fermion running in the loop, and then there was a scalar running in the loop. And the two diagrams were canceling out, right? And the quadratic divergence was canceling out. And the question now is, if I break supersymmetry, who guarantees me that this will still continue to be true, okay? This is absolutely valid question. In fact, the short answer is that whenever you break supersymmetry by analog of the magnetic field, in the other words, whenever you break supersymmetry spontaneously, okay, meaning that your theory is supersymmetric, but the breaking of supersymmetry is the property of your background, of your vacuum. That some field happened to develop expectation value which breaks supersymmetry. Whenever that's the case, then you know that quadratic divergence should still be absent. Of course, you will generate mass splitting for the scalar and fermion, but it will be regulated by the strength of this breaking of the magnetic field. This is the power of spontaneous breaking of symmetries. It's exactly the same way as in standard model, that in standard model, the reason symmetry is broken spontaneously, that's why ultraviolet properties are not spoiled of the standard. In other words, it is very important, as you said, it's very important to break supersymmetry softly. In the other words, to break in such a way that you don't undo the ultraviolet properties of the theory, and in particular ultraviolet sensitivity to the size of the black box. And spontaneous breaking automatically is of that sort, because spontaneous breaking is always an infrared effect. Okay? It cannot change ultraviolet properties of your theory.
I was wondering about the normal or the standard model particles and the SUSY partners. How to determine, for example, for an electron, what the boson or the zelectron, what the spin is, whether it is 0 or 1. What's the way there?
This is to me, or yeah, okay. So again, this is a very good question. So the question is basically, we know that if I identify my electron, there will be a superpartner for sure, which will have a different spin, but how should I identify the spin of the superpartner? In other words, what he's asking is that why can't my electron have a superpartner, not a scalar, but a vector, right? So that's your question. So for instance, and this could have happened because, for instance, I gave you an example when there are two partners, when one is a spin half, and then there is spin 1. So naively, you would say, okay, if this were an electron, in principle, this would be a vector partner. Now, of course, this question is a matter of, in some sense, it's a matter of model building. In some sense, we are lucky that, of course, there are good reasons for it. I mean, once you develop intuition, it becomes obvious that this is the way it should work. But we are lucky in the sense that, as I said, the superfields with no indices are enough to accommodate everybody. And the chiral fermions, already the point, so the fact that electron is a chiral fermion, standard model is chiral, right? So because standard model is chiral, it already tells you that the chiral fermions should be members of chiral multiplets. They should not be members of vector multiplets because gauginos, they are Hermitian, they are non-chiral, okay? So this already tells you that it's better to look in the chiral multiplet. And we look in the chiral multiplet and it works, okay? So in other words, the chiral multiplet well describes electrons, and the partner there is a scalar field, okay? And so therefore, we don't have to go to higher index model building, which some people tried, but it's not extremely successful, okay? So I think at the moment, nobody has any doubts that the MSSM, if it exists at low energies, is well described by chiral multiplets for matter and this type of multiplets for the gauge fields, okay?
Okay, thank you.
I thought that perhaps a component of your question was experimentally, if you had a state that was a candidate superpartner of the electron, how would you know its spin? Was that a component of your question, or yeah? I don't know, if, Albert, if you'd like to say anything.
So you want to make me work too, huh? Okay, so since Gia used up all the chalk, I think
on the far left, there's more chalk.
Okay. In fact, there are. It's experimentally. It's not a simple question. Oh, okay. We have. I found something, but there are techniques to get access. Oh, it's even bigger. Good. Yeah. There are techniques which being thought of now how to get access to spin information of sparticles, let's say. And one typical example I can put is that if you have a decay chain with a squawk going into, say, a quark and a gaugino 2 going then in itself in a lepton, emitting here a lepton, another lepton, and then finally the gaugino, the lowest mass gaugino, which escapes. In fact, there are techniques just to give you the idea of the difficulty, there are techniques to try to catch and see this guy, which is, for example, a partner, the supersymmetric particle of the Z boson, which would have a spin 1/2 in supersymmetry. And you can do that by looking at, you measure this particle, this one escapes, and you measure this quark here. And you can look at combinations, at mass combinations of the quark and the lepton, which are here, and the shape of that distribution is going to be sensitive to the spin which is happening in here. So these are ways of for example, getting the spin. And that, for example, works very well. And there are more complicated ways of also getting at leptons and other things of the spin. But if we were to find, for example, that the partner of the Z is actually different by spin 1/2, then we know we're in a sort of class of models where we have this kind of fermionic type of extra dimensions, so where we have supersymmetry, as opposed to other models with extra dimensions, in which case the particle here would have spin 1. So that's an experimental axis, would be measuring these things, making invariant masses and looking at the shape of it.
Okay, now that Albert's worked hard, does anybody have a nuclear physics question? You're all experts on nuclear physics. Okay, back in the back. Getting good exercise today.
Hi, I had a question about supersymmetry. The supersymmetric particles, do they follow the same laws as the normal particles? I mean QED, QCD, and wake interaction.
I mean, they, well, depends what you mean under the laws. I mean, they have certain charges and certain masses, and they don't violate any principles that are respected by the ordinary particles. In other words, they respect gauge invariance, their interactions are gauge invariant, etc., and Lorentz invariant and Poincare invariant. Unless you break Poincare invariance by some effective condensate. So in that respect, yes, of course, they respect the same laws of physics, but since they have different spins, they interact accordingly to their spin. Yes, I mean, their properties may be very peculiar and extremely different from the properties of the standard model particles. Like, for instance, if you take Gravitino, a partner of the a supersymmetric partner of graviton, which has spin 3/2. It's a fermion, but it's a vector fermion. It also has a vector index. Now, the interaction properties of that fermion are very different from the interaction properties of the standard model fermions. For instance, that fermion couples, because it's a partner of graviton, it also couples like with gravitational strength, meaning that it's an extremely weakly coupled particle. Okay, so in that respect, of course, it's very different and it's very, very interesting. But otherwise, of course, they respect all the fundamental principles that the ordinary particles do. Okay.
Okay, thanks. And do they have the same quantic numbers, excepting the spin?
Do they have the same quantum numbers?
Yes.
Yeah. So if you have, okay, good. So in supersymmetry, there is. Okay. So this is. Yeah. So let's take the chiral multiplet, okay, for simplicity. So let's expand this so we have a scalar electron, and then we have an electron, and these are the physical propagating degrees of freedom, okay? So now you can ask the following question. Obviously, they have different spin. Why? Because super transformations, they affect they are not a direct product extension of Poincare group. Okay, so they change spin. Now your question is, what about other quantum numbers? What about quantum numbers under the internal symmetry groups? Okay, so for instance, charges such as charges, baryon number, lepton number, and different kind of things. Okay, now it turns out that there is one interesting exception of an internal type of a symmetry which looks like internal symmetry. Okay. But under which superpartners may have different quantum numbers. And this is a so-called R symmetry, okay? So now R symmetry is a symmetry under which the fermion, this guy, the chiral fermion itself, the coordinate, they transform, okay? So in other words, under R transformation, the theta parameter itself rotates with certain coefficient, okay, with certain phase. And because theta parameter rotates, in other words, theta parameter itself has a charge. And because theta parameter has a charge, obviously the charges of different partners under the R symmetry should be different, okay? So R symmetry is one example when superpartners, they have different quantum numbers under this symmetry, okay? So under the rest of the internal symmetries, which commute with supersymmetry, which are outside, for instance, the standard model group, gauge symmetry or QCD, or etc., then yes, of course, superpartners will have the same quantum numbers. But R symmetry is an important exception. Okay?
Okay, thanks. And last question. What problems the supersymmetry is solving?
What problem supersymmetry is solving? Supersymmetry is solving, first it's keeping us busy, so that's okay. That's already good. The problems that it's solving is, as I said, yeah, main motivation. So there are different, in other words, what you're asking is that what is the motivation for supersymmetry, okay? Now, of course, there is motivation about any self-consistent physics and symmetries just to understand nature, right? Fundamentally, we keep thinking about all possible symmetries and what are the symmetry extensions of the symmetries of nature that we see around us, etc., etc. Now, why? Because symmetry is a very powerful guideline. It was proven to be very powerful in understanding fundamental principles of nature. Okay, so that's one thing. On its own, it's always important to think about new things. Of course, in mathematical, it's a beautiful structure. Now, as far as physical motivation is concerned, now, first, supersymmetry is already motivated from string theory. Now, motivation for string theory itself is to have a theory of quantum gravity. And it turns out that supersymmetry plays crucial role in formulations of string theory, at least the formulations that we know today. Okay? So, in some sense, you can say that supersymmetry itself is motivated from this realization of quantum gravity. Now, another question is, what about, of course, supersymmetry, as we know, it's a broken symmetry of nature. And the question is, at what scale it is broken? Now, it could be broken at any scale, in principle. The motivation for low energy supersymmetry, why we think that supersymmetry could be broken at low energies, is, as I explained, the hierarchy problem. Because if supersymmetry is broken around TeV energies, then it takes care of the problem of ultraviolet sensitivity of the Higgs mass, okay? Without any need of strong gravity or anything like that, because quadratic divergences cancel out among the superpartners. And this is the motivation for low energy supersymmetry. There is an indirect motivation because low energy supersymmetry also accomplishes this idea about unification of the gauge couplings, because it turns out that in minimal supersymmetric standard model, couplings unify much better than in the non-supersymmetric case. And this is another indirect motivation for having a low energy supersymmetry. Okay?
Okay, thanks.
Yeah.
Again, one question to beyond standard model. How does supersymmetry change the expectation value?
I don't see you. Yeah.
How does supersymmetry change the expectation value of the vacuum?
So let me understand the question. So the question is, vacuum, I don't know what to, so you mean expectation, usually we mean expectation values of some order parameters in the vacuum, okay? So you have different order parameters, and these order parameters, fields, they can be zero in the vacuum, or they may be non-zero in the vacuum. So for instance, in our vacuum, by the way, electromagnetic field, the background that we live in, because of CMB, is on average is non-zero, okay? And so on. So now you are asking, your question is what? How the fact that I have a supersymmetry theory, how this affects the expectation value of certain order parameters? For instance, let's take the Higgs. This is the question. Higgs expectation value in the standard model, for instance?
Yeah, for example, or the vacuum energy.
Oh, the vacuum energy.
Yeah, this
oh, very good. Yeah, yeah. No, that's not an expectation. Yeah, that's a vacuum. So yeah, okay. So the question is about energy of the vacuum, which we didn't address in this question because in these lectures, because these lectures were entirely motivated by LHC and TV physics. But yes, there is this issue with the vacuum energy, which is a big issue. We don't understand why the energy of the vacuum is so small. Okay. So currently, actually the energy of the vacuum, if you wait, well, actually vacuum you cannot wait in the lab, but if you deduce the energy of the vacuum from cosmology, the energy is something like 10 to the minus 29 grams per centimeter cube, okay? This is an extraordinary light mass, okay? And it's a very small number. And the frustration is that not just because this is a very small number, but actually it has exactly the same sensitivity to the size of the black box as the Higgs mass. In fact, even worse. The vacuum energy is quartically sensitive to the size of the black box. Okay? So in other words, if I compute a diagram without any legs, the so-called vacuum bubbles, for instance, fermions run here or whoever runs here, this will give me contribution to the vacuum energy which is quartically divergent. Okay? Now, for instance, in supersymmetric theories, one of the very interesting features of supersymmetry is that this, in case of global supersymmetry, in case of local supersymmetry, you also need R symmetry, but never mind. This cancelled. So in other words, energy of the vacuum in global supersymmetry, if you ignore gravity, has to be zero just by consistency with algebra, supersymmetric algebra. Now, this is in some sense good news, but it's also not very good news, because since supersymmetry we know has to be broken. You see, if supersymmetry was unbroken, all the problems would be solved. So, okay, the hierarchy problem, since supersymmetry is broken, we are back to the problem, because the vacuum energy will be set by the scale of supersymmetry breaking, unless we fine-tune it. So therefore, as it is now, supersymmetry can slightly lower the vacuum energy, but it cannot solve this problem completely. Well, it can solve it by 60 orders of magnitude, but there is another 60 remaining. So, okay.
Okay, we have one last question.
In the lectures about the experimental search for the extra dimensions in high dimensional theories. So I wanted to ask you: is there any experiment attempt to find the extra dimension in supersymmetric theories? It means that the fermionic coordinates to look for the evidence for the existence of the theta coordinate.
Essentially, he's asking. Effectively, you're asking about the experimental search of supersymmetry, right?
I mean that because in the there's some experiment to want to find out the existence of the extra dimensions, for example, in Kawasaki lens or something like that. So, is there any experiment to want to find out the evidence for the theta coordinate?
Theta coordinate.
Yeah.
Yeah, that would be equivalent of looking for supersymmetry. So why don't you
supersymmetry. Actually, I explained in the lectures that's one of our high search programs or high profile things. So certainly, if the question is equivalent, if we discover supersymmetry experimentally by answering this question, then yeah, for sure, this is big teams in the experiments are working on. And I gave in the first lecture yesterday several examples of how we actually tackle that question and how we can see these signatures for supersymmetry. In fact, if there is low energy supersymmetry, it should be easy, quote unquote, for the experiments to see that by this extra production of particles and these decays that you're going to see. So yeah, absolutely, that's a high part of the program for searches.
I mean, if you want to make analog with, in your question, with extra dimensions, right? So basically, the analog of, sorry, thank you. The analog of, we search for extra dimensions, direct search for extra dimension is through trying to find Kaluza-Klein excitations of ordinary particles, right? So analog of Kaluza-Klein excitation in case of supersymmetry would be a superpartner, okay? So you can think, if you want to make this crude analogy, well, it's not very crude actually. If you want to make this analogy, the analog of superpartner in search for supersymmetry, experimental search, is the analog of Kaluza-Klein in case of normal bosonic extra dimensions, okay? I don't know if this answers your question.
Okay, with there, let's thank the speakers again.